Bonjour, my name is Eli Burstein. I work at Google, where I lead the anti-abuse research team. And today I'm going to talk to you about the SHA-1 collision, obviously. It has been a long and interesting journey over the last 3 years while we created this first collision. This is a joint work with a bunch of few people, including Mark Stevens, the mastermind behind it, Pierre Kapperman, Ange Albertini, Jarek Markov, and Alex Petit-Bianco. Before we get started, to make sure everyone is on the same page, let me quickly recap what the hash function is. So what is a hash function is? It's basically a function which will take a file of arbitrary length and will reduce it to a fixed size string, which we call a digest or a hash. This hash has two specific properties which are very important for security. The first one is hash uniqueness, which means if you were to hash two files, even if they have 1 bit of differences, the hash will be drastically different. The second one is one-way function, meaning that from the hash, you do not learn anything from the file you've been hashed. That's very useful for if you're sharing a sample or so forth. So that's why the basic cryptographic property of a hash function. So where do you find hash function? Well, you find them pretty much everywhere. They are used in document and software signing, for example, to verify the integrity of the Windows update. They are also used, obviously, into HTTPS certificate to make sure your certificate is valid and has been signed by a CA. They are used in version control for integrity purposes and do deltas, and obviously they are used in backup for integrity purposes. They're also used in a slew of softwares, including databases, sometimes file system, legacy system, and whatnot. And this huge diversity of software who use hash functions explain why it's so hard to understand what is the consequences of a collision, because we can't know for sure who is using it. I'm going to talk to that a bit later. So today I want to go through 3 points with you guys. The first one is we're going to talk about the past, and we're going to talk about what are hash functions and how they've been used and attacked in the past, mainly drawing from the MD5 example, which was the biggest break before ours. Then we're going to talk about how we found the SHA-1 collision, how we did it, and what was the complexity behind it. And finally, we're going to look forward, and we're going to talk about a post-collision world. What happened next, what is going to happen, and in particular, for everyone running software, how to deal with legacy software. We still use SHA-1, and what does the future hold for hash security as a whole. So before getting started, a quick show of hand. How many of you know what a collision attack is? Okay. How many of you know what a pre-image attack is? Way less. Okay. How many of you know what is the difference between the pre-image and the second pre-image attack? Even less people. Okay, so let's go briefly around what they are so everyone knows what we are talking about, and then we go into how we do that. Before I want to do that, I want to give credit to everyone. While I'm the one standing in the room and talking to you about SHA-1 collision, it's important to remind that it's a collective effort. Actually, that's the last piece of a puzzle. The cryptanalysis of SHA-1 started about 15 years ago, and 2 people stand out of the community who did research. The first one is Wang. She's the one who brought all the theory behind how to break MD5 and SHA-1 and create collision. So she's the one who should be credited for breaking SHA-1 in theory and as well MD5. The other person who stood as a giant is Mark Stevens, my co-collaborator and really the mastermind of the project. He's the one who, for the last 10 years, have been carrying the flag for the entire community and never drop and keep pushing forward until we reach this final milestone. As a matter of fact, many people dropped out. This is my second attempt at breaking SHA-1, by the way. When I was at Stanford in 2008 and 2010, I briefly considered the idea with Dan Bonnet to actually go after SHA-1 and try to enter the race. And we looked at the complexity of the attack and the need of resources, and we're like, that's too hard. Can't do it. And then we've been discouraged and give up. And we reconnected when I joined Google. After a few years, I joined Google with Mark in 2014, and we're like, well, I think we can help you, and we can put at your disposal the technical mean and resources to help you finish this project, and we've been working on that, and I'm really glad we could help him. But I show you that many people actually were afraid of that, and I show how much Mark was instrumental into this. And so if one person needs to be credited for that, that should not be us, that should be him. So I really wanted to make that very clear to people, because while he can't be there today, he's the one who is behind me and actually is the one who did most of the thinking behind that. Okay, so how do you attack hash function? Well, as I said, there is 3 types of attack. The first one is called a collision attack. That's the one we're going to talk in detail today. The idea is the attacker has one file, and then his goal is to create a second file who hash to the same hash, right? So 2 files will have the same hash. That's the collision attack. A pre-image attack is a little bit different. You have an unknown file, and you know the hash, and the attacker has to come up with a file which actually is able to hash to the same thing. So you don't know the file. A second pre-image attack, which is the most confusing, at least in the documentation, is this idea of a known file. Let's say an SSL certificate, and then it has been issued, and you are creating a file which will hash to the same thing while hopefully preserving structures. Both pre-image and second pre-image attack are not feasible in practice. That is why I'm not going to cover in detail, discuss them too much in this talk, but they do exist. It's just for understanding that there are other attacks which are more dangerous. So of the 3, the collision attack is the easiest one to do, and that's the only one which is today available in practice, whether it's for MD5 or SHA-1. And let's get started. So how do you create a collision? Well, the first thing which is very important to explain is you cannot use brute force. While the number we publish are like very huge, in reality, if you were to just say, let's put as much resources I want to break this thing, you can't. The reason for that is we estimate that if you were to do brute force attack, you will need 12 million years of GPU to do 1 collision. Obviously, no one has this power. It's not feasible on Earth, so you can't do brute force. Brute force attacks are impractical, so you need something called cryptanalysis, which is the offensive part of cryptography to understand the flow of the algorithm and exploit them to reduce the complexity. So cryptanalysis use a number of set of techniques, and I'm going to show you a high-level overview to be able to reduce the attack complexity to a manageable form. In our case, that will be 2 to the 63, which is, again, trillions and trillions of computation, but it's still more manageable than those 12 million years of GPU that no one can do. So no cryptanalysis for a function, no break. So how do you attack a hash function? The first thing to understand is how a hash function is constructed. There is 2 things. There is a construction of the hash function, and there is a compression function. The construction of the hash function is the mechanics by which it's able to reduce an arbitrary length file into a fixed size hash. So in the case of SHA-1, we use the Merkle-Damgard construction, which was invented by Merkle during his PhD in 1979. It works as follows. You start with initialization vectors, which is known, and you take the first block of the file, and you pass both into what we call the compress function. In our case, that will be the SHA-1 compress function. Then you take this output and feed it again to the compress function with the second block. So now you have reduced 2 blocks into a fixed size, and you keep going and going until you reach the last block. And when you reach the last block, you basically have successfully reduced your entire file, where, depending how many blocks you have, into a single string that we call the hash, right? This is the construction of them as a Merkle-Damgard construction. It also works, this is the same one which is used both for MD5 as well as SHA-256 and every SHA-2 family members. Okay, so the important thing to understand there is by looking at the picture, and you can see it very clearly, there is no dependency between the blocks. So if you look at the SHA-1 compression, it only depends on the input of the previous block compression and the block itself. So there is no dependency from previous block or past block, which means that if you were to attack it, all you have to do is focus on 1 block at a time, which makes it in a way more easier because there is no nonlinear dependency. So how do you attack the SHA-1 compression functions? Well, let's take a look at that. Here is a very non-traditional way to represent SHA-1. If you look at the Wikipedia page, you will not see this one. This is the cryptanalysis version of SHA-1. What we do is we unroll the entire function, all the 80 steps, and we lay them out because we need to understand very precisely how the bits are moving at each step along the way to be able to understand how we can control them and reduce the entropy generated by the function. So that's exactly the same compression function I showed you. You can see the block on the top and the chain value at the bottom. That's the same thing, except it's unrolled. The purple box do represent the scrambling part of the function. For example, f is a nonlinear function which allows you to permute blocks, and the plus is the addition 32 bits. So basically, this is the thing which is responsible for scrambling the bits and compressing it to the short string. Okay, so how do you attack that? I'm going to skip over a lot of detail. There is 15 years of cryptanalysis, so I can't really go into detail, and personally I don't know all of them myself. I just want to give you an overview of how cryptanalysis works so you can follow along with the rest of the talk. So the cryptanalysis works as follows. We look at what we call message differential paths, which is this idea of can we study when you input a class of messages, how the bit has changed and how the difference are propagated along the function. This is represented into the diagram with red blocks. We have been able to study them very carefully, and along the year, we were able to actually solve the first 16 steps. So for us, the complexity and the entropy, if you will, of the function has been pushed back by 16 steps, making it the function less complicated to attack. And then after 16 steps, we have a few more steps, which is about 8 steps where we can't really predict what will happen, but we have a bunch of techniques to help control how the binary, the bit will diverge. Not fully, but enough to control it a little bit. We use, for example, boomerang, neutral bits, which basically helps you to, by flipping there or there, being able to control how much the complexity explodes. And then, well, we don't know. That's what it is. The red part is the part where we have to do this very expensive computation. Is we have been able to push back the complexity to only a fraction of the function, still a big fraction, but we are able to push it back, as you can see on the diagram, and that's why it's not a brute force attack, right? I hope it gives you the intuition that by able to understanding how the function works, we're able to reduce the steps where we don't know what happened to a minimal amount we can, so we reduce the computation cost. Fair enough? All right, I see a lot of people nodding. Good. All right, so let's move in. Okay, so I lied. I'm a liar, sorry. What happened is, in reality, when you do a collision, you don't do one block, you do 2 blocks. Actually, that's what Wang's main idea. So she's the one who came up with the technique. It turns out it's easier to do a collision with 2 blocks than 1 block. So the way it works is we have the file, and we have the first block, and it doesn't matter. This is just your prefix, and you can do whatever you want there. Then you have a first block, what we call a near collision. So the near collision is basically you find 2 blocks on 2 different files, which are almost the same. Almost the same for a notion of distance and constraint, which means those 2 are, we believe we can glue them together back to cancel out the differences. And this is the collision itself. So first we find a block which is producing us close to the result, and then we have this thing which finally resolves all the differences. And then remember, there is no dependency between the blocks. So when you're done with the collision and all the differences have been resolved, you can basically put whatever you want. Because obviously when the collision is done, the 2 have the same output, so collision is complete. So one of the things which is the most misunderstood about collision attack is the suffix can be whatever you want, and even after you found the collision, you can swap it for anything you want because it doesn't matter, right? That's why people were confused when we released the attack, say we can create as many documents as we want, is because we can swap the suffixes to whatever we want by appending the collision blocks to it. So we'll be able to create many documents as we want. I will show you a demo of that. All right. So now that we kind of know how to do collision, I'm not going to give you more details than that because I think it helps. I think you have the idea by now. Let me tell you how you exploit them and how you make them useful. So the first type of attack we have when you have a collision is called the fixed prefix attack. This is the one we use in SHA-1. In that case, we have a prefix that you have to choose before you create a collision because it's going to be, remember, the input of the prefix will be used in the collision, so we can't change it after the fact. Then you have the blocks, which is where you do all your computation, and those are pretty like random blocks. And then you have the arbitrary suffix that you can change as long as they are the same. They are the same, but you can swap them as much as you want. It doesn't seem very powerful at first glance, but actually there is a very neat trick, which is if you craft a prefix ahead of time which is specific enough, you can use it to display things which are not the same. So the idea would be you use the collision block, let's say, for the length of a JPEG comment as we did. In that case, the first collision will point to a part of the suffix, whereas the other block will point to another part. And as a result, you will display things which are different while having the same SHA-1. So it's not the files are different. They're only different at the collision blocks, but they are displaying different things, so you can trick people, let's say, with a lease contract, 2 different terms and so forth. That's the basic idea of why spending a lot of time on finding the right prefixes was very important. The other option, which only worked for MD5, but it's worth mentioning because there was quite a few interesting attacks about it, was when you can actually choose the prefix. In that specific case, you relax the assumption, and actually, the prefix can be different in both cases, so it gives you way more flexibility where you can actually do whatever you want before the collision, and whatever you want after the collision, and give you way more flexibility. And when you have this kind of power, a lot of things open up. So let me walk you through two concrete examples and illustrate that better. So let me show you two, because a lot of people say, well, collision is more in the academic world and it doesn't have real world consequences. They do. So these are the two from MD5 because we have the history of time in front of us and we can look at examples from the past. SHA-1 is too recent to see this kind of attack yet. So the first one is the MD5 SSL certificate forgery. So in 2009, Mark Stevens and Alex Sorotyov and a bunch of people were able to create a signing certificate by using an MD5 collision. So how that works? Well, here's what a certificate looks like. So when you buy a certificate or when you get one from Let's Encrypt, you will get something which have a serial number, a validity period which tells you when it's going to expire, and then a real cert domain name, which is basically what is your certificate is valid for, let's say mydomain.com. And then you have a bunch of other information. One of them is, of course, your RSA public key for the cryptography, something which is called extension. They are in green, which basically say you cannot sign other certificate. Obviously, you're not a CA. And finally, the signature, which is using, at that point, MD5, which basically is a way the browser verifies that your certificate has been signed by a valid authority and make it valid, right? So that's the thing you have. So how do you exploit that with a collision? Well, the first thing is you choose a prefix where you basically add the serial number and the validity period at the back. Then you're going to change the real domain name to the one you want, and in that case you want star, meaning you can sign for everything. That will be way better. The certificate will work for everything. Then you add your new RSA public key, which is the one you want to use to sign the certificate with, your certificate key. Then you have to change the extension and say, actually, this is a signing certificate, because you also want to be able to delegate and create new certificate. And finally, you have to push back everything, right? Because remember, we have to keep the same data, so you have to both put the collision and you also have to put back the rest of the certificate. So how you do that? Well, you use what we call the Netscape comment extension. So it turns out there is one extension for SSL certificates, which is called the comment extension. No browser cares about it, but it exists. So the idea is you push the old private key, the old public key, sorry, as well as some other information directly into the comment extension, so there are no nullify. And this is where you put your collision. And then all you have left to do is to put back the same signature. The signature would validate because they do a checksum on using MD5, and you have a signed certificate. This is how you create a colliding certificate. You're like, wow, okay, that seems very complicated. No one is going to do that in practice, right? Well, not true. In 2012, I believe, there was a report of a super malware called Flame. Flame was used to infect Iranian computer. And what makes Flame unique, and you can see it on the screen, was a use of a colliding certificate. The colliding certificate was actually a Microsoft terminal server certificate which was used, lifted, and repackaged to actually be used to sign fake Windows update. So they were using collision to be able to actually push fake Windows update and then fake computers that way. This is the first and only weaponization of collision we know of, but it showcases that actually collision can have real-world impact. For trivia, okay, mic changing. Can you turn it? Awesome. All right. So, sorry about that. So So for the trivia, what's very interesting about this, this case is Mark and a few cryptographers created a foreign. All right, we are a little bit unlucky today. All right, great. So what's interesting is when Mark and a few people look at the forensic analysis of the certificate being used, of course, obviously there was a collision, except the collision didn't use 2 blocks, as I told you, but 4. And you're like, why would they use 4? Well, it turned out that's a very suboptimal way to create a collision. The certificate dates back from 2009, and if you remember, I told you the collision was published in 2009. So someone, somewhere, well-funded and well-versed in cryptography, have developed their own way to create SSL certificate collision. It was not as efficient as the one which was developed by academia, but it was nevertheless working, and they created their own collision. So we know from the forensic analysis of the certificate that the people, when they lifted the certificate in 2009, used their own cryptographic knowledge and tools to create this copy. Who that might be, I leave you guys up to guess, but these are clearly people who knew what they were doing. Yes, it was a little bit suboptimal, but it did the job quite well, and so this is the only example we have of a weaponization of a collision, but they do occur in practice, which is why collision needs to be taken seriously by everyone. At least that's a good example of why it's important. All right, so to recap, where do we stand today? MD5 is broken. It's like literally 3 operations. That's horrible. MD5 has been broken for a long time. It is to the point where you can do it on your cell phone. You can literally create a MD5 collision on your cell phone if you would like. For SHA-1, which is our new result, you need 2 to the 63 computation, which is a few trillions of computation, so you can't do that on your cell phone. You need a data center for that, but you can do that. And I also added on the right side the security for pre-image attacks, and as you can see, while there are some numbers which are lower than the security claims, they are so high that they are completely unpractical. So that's where we stand today for the old generation of hash function. I'll talk about the new one at the end of the talk. Okay, so how we went about finding a SHA-1 collision. So the first thing is you need a plan, and so after we talked with Mark in 2014, as I said, the first thing you have to do is choose carefully what prefix you want, because you're going to compute a collision based of it, and you can't change it after the fact, so you need to be pretty sure of what you're going to do. The person who created the prefix for us was Angel Bertini from our team, who came up with a very clever idea of combining PDF and JPEG to actually be able to create a very nice way to swap images and show different things. And so he created the prefixes. And then during the 2015 and 2016, we ran the first phase of the computation, which was finding, if you remember, the near collision block. At that time, the Google GPU infrastructure was not yet ready to sustain that kind of computation. So instead of trying to test something which was ready for production, I opted out to use CPU. So we used about 300,000 CPU for about 8 months to be able to compute the near collision. Then 2016 was the most exciting year. We had to develop the full attack, so we got the near collision back, and it was, I think, in February 2016. And from there, mainly Mark and Pierre worked on to developing the full attack. It was also, I will say, the most eventful part because we encounter unforeseen difficulties. And then in 2016, we leveraged the GPU infrastructure of Google to do the second phase of the computation. We had to use way less resources because at that time, GPU were more efficient for cryptanalysis if you program them correctly. And so we use only a few thousand there. All right, so what Ange came up as prefixes was this idea that we're going to have a PDF header, which will contain a JPEG header because PDF is like a Russian doll. It has a lot of frame, and then you can embed whatever format you want in it. And the JPEG header will have a comment, and we will put the collision block at the border of the length of the comment. So what it will do is the length of the first file will go to one place, and then hopefully The second block, which is different, will point to another place, which gives us this flexibility to point to different part of the suffixes. So at that point, we have this ability to swap one another. So it has been tested extensively, and then when we were confident it will work, we use that as a prefix. Then I worked to help Mark to port his code to Google infrastructure. And a few interesting engineering tidbits are, one, we had to find the right trade-off between the size of the batch of computation. So you have to choose between failure and efficiency. So the more you distribute your code, the more it costs. The longer you run, the more efficient it is, but you run into the risk of having fail CPU, fail machine, reboot, preemption, whatever, and whatnot. So we settled on to have like batch of 1 hour. So we would do 1 hour of computation, save the result, 1 hour of computation, and repeat and repeat. One thing we did early on, and I think that was really the saving grace, was to be able to have code which runs stateless. So the original code has a way to distribute which computation you will do. We started to use a random generator and try to distribute the code without being able to restart it without synchronization. That saves us the headache of having failover and a database for synchronization and pushing things and the capped TRM. So stateless was way easier to distribute and fan out. And finally, that was my first large-scale computation as is. So I thought MapReduce was awesome. And you have this huge hammer. It's like, oh, it's going to be, you map everything and then you reduce the potential solution. Seems a great idea. It turned out it's a horrible idea. I ended up with what we call strangling. You can see it on the graph. Basically, most of the computation happened, and then we have a few shards, which is a part of the computation, which are not done and can be rerun. And because you don't use the full capacity of your job, you are losing a lot of time. So it was really not efficient. For the second part of the attack, we moved to a client, a factory design pattern where we have a producer and then we run a bunch of jobs, and they are all distributed and independent, and you return. And it was way more efficient. So we learned a lot during this first phase, and it influenced a lot how we did the second one. Okay, so in 2016, sent an email to Mark. We found it. Here's the blog. I was really excited. We have our first near collision. We know it's going somewhere. Mark said, give me a few days. I'm going to look at it, make sure everything is fine. I'm like, okay. And then Mark came back to me and like, I think we have a problem. I'm like, okay. What happened was the block we found using the traditional approach we had in mind didn't work out because it was over-determined, meaning that we couldn't find a potential solution, so we couldn't find a way to resolve it to the full collision. It was okay. We actually decided to use novel trick, and Mark and Pierre spent months trying to figure out novel ways to actually use size solving to actually make it solvable, but the first few weeks were a little bit, we were sweating a lot because we thought we might have to redo everything or it might be impossible. So the fact that we encountered this difficulty, which we believe will happen to anyone trying to do a collision and no one mentioned them before, led us to believe that actually no one ever reached the completion of phase 1 because they would have had to face the same problem. Anyway, long story short, they fixed it, found a good way to do the speed up using the boomerang attack and so forth. That's what you have here. And the two tile boxes are basically the extra step we did for step 2, which is like finding this additional condition and fixing the solvability issue. And we wrote the attack code, mostly Pierre and Yarrick, in GPU, and then we were good to go to run the final computation. So final computation took place into GPUs. And one of the interesting properties of GPU is that we can't do what we did with CPU. With CPU, what we do end-to-end, and then come back and do another end-to-end, another end-to-end. For GPU, because of the memory transfer, you can't really do that. So Pierre and Mark come up with this great idea of we're going to advance step by step. So you remember there is 80 steps. So what we do, it will generate all potential next step, like or at least enough to fill out the GPU buffer, then compute all the step forward, and then when we have exhausted our pool, if we couldn't find anyone, backtrack. And so we would fill, backtrack, fill, backtrack, fill, backtrack. So the reason why you want to do this is because it helps to maximize the use of the GPU memory and do parallelization while having to limit the number of wiping the memory and filling it out again. You really want to do it sequentially and minimize the memory transfers. So we had one instruction and multiple thread, which was exactly what we wanted. To give you an idea of how the complexity increase. In SHA-1, this is a graph, so it's in logarithmic scales. And you can see that when you are at step 14, you have about 50,000 potential solutions. And then you go up, and you remember it blew up right after that. So you have 100 million, and then you have tens million, and then you have 100 million, and then you have a trillion, and you have tens of trillions, and then you reach a point which is roughly around step 22, 23, where this is the maximum computation cost, and then it fairly goes down, and then you reach the last point, which is where basically you found your collision, right? So the initial phase, because there is so few solutions to compute CPU, so large middle thing in GPU, and then the last stage will be in CPU. All right, so all that said and done, the new attack we call Shattered took about 110 years of GPU. That's how much it took. Way less, as we mentioned in the early part of the talk, of the 12 million years you would need for brute force. So it was way more efficient. Still a large computation, one of the largest we believe today. And we got our collision, almost. What happened is then we send an email to Mark, hey, we found it, yay. We were super excited with Yarek. And then he wrote back a few hours later, he's like, that doesn't work. We're like, what? Like, yes, it doesn't work. And then he realized that we had a big Indian, little Indian problem. We were computing in one, and he was expecting another format. So it took us like a day of like crisis mode to figure that out. And then it's all resolved, and it was working. And then he sent us the first 2 PDF, which had the same SHA-1, and everything was fine. But again, this was like the second time we were sweating bullets, and I'm like, I'm done with that. So here you have it. This is the 2 first PDF we released to the world. You may have seen them. They're on shatter.io if you want them, where you have 2 PDFs which have the same SHA-1 and yet have display 2 different things and have 2 distinct SHA-256. And when we release the website, we say, well, in 90 days we're going to release the code to actually create those PDFs yourself. Remember, you can swipe the suffixes as much as you want, so you can remove any image and put anything. So we said, in 90 days, we give people fair notice, disclosure policy, all that. Turned out, 2 days after, the internet come up with a better tool than ours, so that's the one we use for demo. I'll do a short demo for you to show you how it's easy when you have a collision to do with 2 images. So if we have a cat and we have a tiger and we want to embed them, so those are 2 PDF. And as you can see in a second, they will have the same, they have distinct SHA-1s, right? That's the 2 basic things. So now what we're going to do is we're going to use the collision to embed both of them into a single PDF and use the collision. So you use the code, as I said, from the internet. You have the link below. And then if you look at what happened, and you see it's very fast, now both of them have the same SHA-1. And they will display either the tiger or the cat by embedding both of them. And if you were to look at the SHA-256, well, not the same. So that's basically how you can create your own collision at home. Download the code, you can do it yourself. 3 keys out of the bag. So now everyone can now create the thing. This is, of course, a fun example of how you would do it. You can imagine nefarious purposes attacks where you have, let's say, a rent contract, and you sign something which says you're going to pay $1,000, and then lo and behold, the other one said you have to pay $10,000. So basically having using SHA-1 for any kind of integrity is now kind of, at least for PDF, is kind of pointless because you can't trust it. And so it defeats. So how does that work behind the scenes? So just to give you like a clean outline. Actually, this is something which was done by Hector Martin. He did that a few days after we released the attack. He was kind enough to give us permission to reuse his diagram. That's the best one we come up with. Way better than the one I did. So I'm going to use this one. So in the red, on the left side, you see this is a fixed part. This is our chosen prefix and the collision block. And the green part is the part you can swap. So on the top, as I mentioned, we have the PDF headers. And then below it, we have the JPEG header. And then you have the JPEG comment, right? And the JPEG comment have a length. And the length is at the border of the collision block, right? So obviously, in one file, it is 73. On the other file, it is 170F. And obviously, different block length for comment mean we have desynchronized what is displayed in both files. While they have the same suffixes, they are desynchronized. And so in one case, you would have a comment and the next image will show way lower into the content. In the other case, it will show the first images. So that's how we embed two images and show one or the other. That's how the trick works. So I hope this illustrates a little bit better what is happening behind the scene and how you can use one collision and use it to create many, many colliding PDFs. Yeah, JPEG commands your side, as I mentioned. Okay. Post-collision world. So what happened next? Well, first thing, the most important thing for us was, and that's the reason why we thought it was really important to do a collision, is Mozilla decided to give up on SHA-1. Thanks to them, they gave up a few days right after the announcement of the collision. And they deprecated ahead of schedule. That was really important. There was rumors that we might extend the lifetime of SHA-1. And I think that was the final nail on the coffin. So that's the great outcome we wanted to have. Microsoft did follow in May. And was again crediting us into the advisory for pushing it further. So we're glad that now every browser in the world do not use SHA-1 certificate, and I think that's a good thing for the world. So that was the main thing we wanted to achieve. So that's great. We got leaked. I don't know what happened, but someone placed a very large bet about 24 hours before we released the attack publicly, saying yes, SHA-1 will be broken in 2017. So the guy cashed out, I think, something like gained like 8 or 9 bitcoins. So basically, someone found it out. Mark, in the early morning of the announcement, struggled with Ethereum, but was able to cash out the bug bounty. So Mark was able to cash out the bounty we had for the SHA-1 collision. Not a lot of Bitcoin, but still nice for him to get it. This is the unforeseen consequences I was mentioning too. Someone who is working on WebKit decided to test if WebKit would be not vulnerable to collision attack because WebKit used SHA-1. So he submitted a unit test to the SVN of WebKit, and then it was gone. It like literally destroys the entire WebKit SVN directory for 8 hours. No more WebKit. Everyone was freaked out. It turned out there was a huge bug into SVN, which actually do not work well with SHA-1 collision. It used SHA-1 for integrity, was never meant to withstand collision, so it completely collapsed. And then Apache reacted very quickly and said, hey, please patch, and do not be careful because you might destroy your repository if you do that. You can recover it, but it's way more tedious than a normal command because everything is completely messed up. So that was this watershed consequences I was alluded earlier. This is the one we know of. There may be a ton of legacy software, especially in corporations, that we don't know of, where collision might trigger weird bugs that we are not aware of. So that brings up the question of what do you do, right? I mean, collisions are in the wild, and maybe you have a legacy software, so what do you do? Well, happened to Git. It turns out that despite people warning Linus Torvalds that you should not use SHA-1 in 2005, you're like, nope, I'm going to use it. And so now they are slowly transitioning it out of Git, but it's really complicated because it's really backed into the system and they have a lot of assumption around it. So what do? You use something which we call counter cryptanalysis. So remember, I told you the way we compute a collision is very specific with differential paths. So there are places where the difference, and you can see it on the screen, cancel out, and they are very, very noticeable. There is also other clue. So it turned out that Mark developed a very nice technique where you can actually, with a single file, test if it's part of a collision or not. And it's a little bit expensive, about 2 or 3 times more expensive than normal SHA-1, but it will tell you if there is a collision. So you can use that to test for collision. And it has very, very little false positive. I say it's like 0.000000001. So you can use it and basically believe in it. And it works both for SHA-1 and MD5. So that's something that you can deploy if you are still using SHA-1 anywhere. That's what we did. And that's what also GitHub did. So a Googler actually patched git to make sure that when you submit something to Git, if there is a collision, it will reject the commit. And in March, GitHub did the same. They announced it in their blog post. They started to use Mark Stevens' code to actually detect collision and say, if you are trying to submit something which has a collision file in it, we're going to reject it. So GitHub was protected while Git was patched. And then in 2012, Git also now include cryptanalysis as well. They made recently another patch to improve it. So now we do have cryptanalysis, counter-cryptanalysis also backed into Git, which is how we deal with legacy software. Last thing I wanted to mention is we also took the decision to scan any incoming document both for Gmail and Drive early on because we don't know what our clients use. Some might use old clients which might trigger a bug we don't know of. So better safe than sorry. So if you were to try to send any collisions to Gmail, you would see the warnings that you see here. And as I said, the reason why you might want to scan for collision as well is it crashed legacy client software. It does. Like SVN literally was brought to its knee. Colliding documents might be used for nefarious purposes, like I told you the rent example, might be other one like contract or instruction or password or whatever you want, and black swan, which is unforeseen consequences that we don't know of, so rather than to face them, we rather pay the price and scan up. How much do we pay? We have tested on 1 billion document. This is the sample we tested with and without it. It's about 4.4% overhead for us. We still believe it's well worth it to scan every incoming PDF document to protect our users. So I would strongly encourage you to do the same if you deal with document and you SHA-1 somewhere. So where does that leave us for the future? Well, future looks great. We have 3 different types of hash functions that we believe will be very useful. We have SHA-256, which is a natural replacement of SHA-1. Then we have SHA-3, which have been a completely different form of function, which is really good. It's used as sponge construction, so very different from the SHA-2, so we have a lot of diversity. And we also have Blake, which is another hash function, very fast, and Blake 2. So we have a lot of diversity and a lot of good options to choose from. So basically, we have all the tools to mitigate the next collision when it will happen. And so we are in a very good place. So it's a very, it's a transition period, but the future looks amazing. And just the takeaway for you, SHA-1 is dead. Please do not use SHA-1, please. If you use still vendor, security vendor who still use SHA-1 as a certificate, please tell them to stop do that. Counter-cryptanalysis is a very interesting tool. I don't know if you heard about it before, but that's very something you should add to your detection if you are dealing with document and integrity and stuff like this. And finally, the future looks great. We have a lot of hash diversity, a lot of good construction, and that's where having good funding for academia who do cryptographic research is important because they are working ahead of the curve. And when we need new algorithms, they are here for us to use. So that's why cryptographic research is more important now than ever. We can't rely on current standard. We already need to think about new standard, what will happen with the post-quantum world and so forth. So we are ahead of the curve. And because cryptography is so important for security around the world and the internet in particular. So I'll take a few questions. I think I have time for 1 or 2 questions. Also, if you are here today, our team have 2 more talks. I encourage you to come and see us. Today we have tracking ransomware end-to-end at 5, and tomorrow we'll have a talk about attacking encrypted USB. So if you are, I would love to see you there as well. And with that, I will take some questions. Thank you very much.